Okay. Good evening, everyone. Today we'll see how to solve a problem on reducing quadratic form to canonical form. Okay, using congruent transformation or linear transformation, I'm talking about. So any quadratic form can be written as x transpose ax. Okay. Here capital X is nothing but x1, x2, x3. Quotient matrix, how do I form it? All of you know. Otherwise, just check the procedure of how to find the quotient matrix. All the square elements come in the diagonal. Whatever combination elements are there, I have them and write them at their respective places. x12 and x21, I will write the same element. x13, I have the quotient -1 and -1. x13 and x31, I will write 1 and 1. And x1, x2, x3. Okay, I have the quotient matrix. Now, how do I solve this using congruent or linear transformation? Congruent or linear transformation. Okay, what is this is? I rewrite A as IAI and then proceed with doing things. Okay, rewrite A as IAI. Okay, yeah. So what happens here? A is 1, 1 minus 1. If it is a 3 by 3 matrix, guys, I consider 3 by 3 identity elements. Okay, it's a 2 by 2 one. Hence, no. If it's a 4 by 4 one, I'll go with 4 by 4 identity matrices. Since it is a 3 by quotient matrix is a 3 by 3 identity matrix, I go with 3 by 3 matrix. I go with 3 by 3 identity matrices. Okay, if the quotient matrix is 4 by 4, then I go with 4 by 4 identity matrices. That's what I want to say. Of course, all of us are aware of congruent transformation. Whatever row transformations are used to transform A to an diagonal matrix, all those I perform on the pre-multiplied, and whatever column operations I do, I perform them on the post-multiplied identity matrix. Okay. So what would be the row operations that I'll perform to make A into a diagonal matrix on the LHS? 1, 2, 3. That positions only 1, 2, 3 element positions only should be non-zero. Remaining all should be 0. For which the row operations that I'll be performing will be R2 is R2 minus R1. R3 is R3 plus R1. Okay. Hence on the LHS, I will have 1, 1 minus 1. 0, 2 minus 1, 1. 1 minus of minus plus 1, 2. 0, 2, 3 minus 1 is 2. Okay, RHS would be R2 minus R1. Now only the pre-multiplied will vary. So whatever has varied, let me write with a different color so that you will be able to identify, I think. Okay, yeah. So R2 minus R1 would be 0 minus 1, 1 and 0. R3 plus R1 would be 0 plus 1 would be 1, 0 and 1. These have changed. Nothing else will change. Okay, remaining all will be in 1, 0, 0, 0, 1, 0 and 0, 0, 1. I hope I am clear. Okay. Now you see, since A is A transpose is equal to A here, guys. The quotient matrix is a symmetric matrix, because of which whatever row operations I perform, same column operations can be repeated. Okay. C2 I can, because see, in the place of first element in C2, I have 1. From C2, if I subtract C1, then I'll be getting 0 here. If I add C3 to C1, I'll be getting 0. Okay. C2 minus C1. If someone is not clear with the procedure, there is a lecture on procedure as well. Kindly go through it before going through this example. Okay. So what I will be having would be 1, 0. Now I'll write it column wise. 1 minus 1 would be 0. 1 minus 0 would be 1. 2 minus 0 would be 2. Okay. Yeah. Minus 1 plus 1 would be 0. 2 plus or minus whatever with 0 is 2 only. 2 only. Okay. This is equal to 1, 0, 0 minus 1, 1, 0 1, 0, 1. No change in the pre-multiplied because I'm going with column operations. No change in the first column as well. Okay. There's a change with the second column. What is happening? C2 minus C1. So minus 1, 1 and 0. Okay. C3 plus C1. So 1, 0 and 1. Also, guys, I'll just may bring it to your notice. If you transpose this, it matches with the column operations one, provided you do with the set of row and then column subsequently. Okay, fine. Now coming back to making the left hand side quotient matrix into a diagonal matrix, right? So for it to be a diagonal matrix, I should get a 0 here and a 0 here. This 0 is made with row operation. The other 0 can be made with column operation. Okay. So R3 would be what? R3 minus 2R1, 2R2. Okay, R1 again brings a non-zero element where I have to call the pains to make it 0. Okay, in the first element position, right? Yeah. So 1, 0, 0, no change in the second row, 0, 1, 2, 0. I am multiplying the first row, the second row with 2. 0, 2 and 4. 2 minus 2 would be 0. 2 minus 4 would be minus 2. Okay. This is equal to 1, 0, 0, minus 1, 1, 0. No change in the first and the second rows. Only the third row will change. First row I multiply with 2 and subtract it from the third row. So 1 minus 2 would be minus 1. 0 minus 2. Okay. No. 0 minus 0 only it would be. There is no non-zero element in the, right? So this is 0 only. 1 minus 0 would be 1. Okay. Yeah. No change in the, no change in A, no change in the post multiply. 0, 0, 1. Of course, I can guess what would be the next operation and what would be the change in the post multiplied matrix, guys. Okay. It is just C3 is C3 minus 2C2. Okay. So what I will get? 1, 0, 0, 0, 1, 0. C3 minus 2C2. So I multiply this one with 2. Okay. And then subtract it from 3. Okay. So it would be 0. 2 minus 2 would be 0. Of course, minus 2 I will have. This is equal to 1, 0, 0, minus 1, 1, 0, minus 1, 0, 1. Fine. No change in the pre-multiplied. Coming to the post-multiplied, what I will have would be 1, 0, 0. I can look at this and write, guys, it is one and the same. Just a transpose of it. 1 minus 1, 1, 0. Okay. And then I'm multiplying second column with 2. So minus 2, 2 and 0. Okay. So 1 minus of, okay, just a second. Let's scroll down. Yeah. C3 minus 2C2. C3 1 minus of minus would be what? Plus. Okay. Yeah. Minus of minus would be 1. Minus of minus would be plus. So I'll have a 3. 0 minus 2 would give me, 0 minus 2 would give me minus 2 and 1. There is some change. Just a second. Let me look at it. What I have done here is R3 in the place. R3 is R3 minus R2. So R3 is 0, 0 minus 2. This is 2 and this is minus 4. Okay. So, no, this is what? This is 2 and this is minus 4. So this becomes 0 and minus 4 becomes minus 2. Fine. Here, what about here? Here, what I have done? R3 minus 2 R2. Na? R3 is what? 1, 0, 1. Na? 2 R2 is what? Minus 2, 2 and 0. I'm sorry, guys. I think I just skipped here. Okay. I didn't do anything with the pre-multiplied one. Okay. Yeah. Minus 2. 2 and 0 is the second row. First row is 1. Okay. So 1 minus 1 is 1 minus of minus 2 is 3. This is, guys. I'm sorry. There is an error here. This is 3. 0 minus 2 would be minus 2, guys, here. 0 minus 2 would be minus 2. 1 minus 0 is 1. Okay, so what exactly I'm trying to say is whatever matrix I have got in the pre-multiplied, I mean the resultant matrix, its transpose would give me the post-multiplied one is what I was about to say. But then since I made an error, I was not getting it. So I was checking for where I missed it out. Okay, so we can just check this. It's just the transpose of it. Or in other words, just see here. I have got a diagonal matrix, P transpose AP kind I have got is what I'm trying to say. Now, what would be the canonical form? Canonical form would be something like Y transpose dy. Okay. What would be Y? Where Y is nothing but something like Y1, Y2, Y3. Okay. Yeah. A and D are congruent matrices, guys. That's why it's called congruent matrices. Why? Because D is obtained after a set of elementary transformations on A. So such matrices would be called congruent matrices. A and D both are same, but then if I reverse back all the operations, I can get back A as well. They are not equal, but they are congruent. So this transformation is also called congruent transformation. Okay. Yeah. So what will I get as Y1, Y2, Y3, transpose of capital Y. And then the diagonal matrix. Of course, I can just write the diagonal elements as well, guys. But anyways, this is the resultant matrix that I've got. Y1, Y2, Y3. If you multiply, what I will be left with is Y1 squared plus Y2 squared minus 2Y3 squared. Okay. Hence, this is called sum of squares form. Sum of only squares are there. The combination terms are missing. I mean, I made the transformation like that, not missing. I made the congruent transformation in such a way that, okay, now you can see how many positive, how many negatives, what is the combination that decides the nature. Nature is what? Indefinite, because I have all combinations. Indefinite is where I have positives, negatives, also zero, right? So it is nature is indefinite. Next, rank is 3. Rank or a small r some people will use is 3. And then what is index? The number of positive terms is index. Index is 2. Signature is the difference between the positive and the negative terms. How many positive terms are there? 2 positive terms are there. 1 negative term is there. Hence the signature is 1. This is how I will find out or I will reduce a quadratic form to canonical form using congruent transformation. Okay. Okay. Thank you.